Hi everyone, this is Mrs. J, and today we're going to be graphing tangent. Alright, I have a quick warm-up for you guys, so please pause the video and give it a try. Alright, go ahead and check your work here. So filling out the t-chart should be okay, but I think taking those coordinates and turning it into the graph was probably a bit tricky because the graph for tangent looks so different than anything we've graphed before. So you do have those three values in the middle, -1, 0, and 1 for the y values. But let's talk about what happens when we have undefined values in graphs. So we learned previously when we were doing rational functions, this can result in one of two things. It could either be a hole in your function or an asymptote. So in this case, tangent actually has asymptotes. It has actually an infinite number of asymptotes because this pattern of this graph is going to repeat infinitely. So you see here, they have an asymptote at -π/2 and then π/2, and you'll notice that the asymptotes are pi units apart, so that would just keep on repeating infinitely to the right and left. So then you can see that for this graph, our graph is negative until it crosses over at 0, 0, and then it stays positive and it approaches our asymptotes from either side. So this is just one period of our tangent graph, but definitely know for these graphs to expect those asymptotes because of the undefined values. So we're going to look again at our parent function for tangent. Here I have a few more periods graph. So you can see we have those asymptotes at -π/2, π/2, 3π/2, -3π/2. So again, the asymptotes are, in this case, pi units apart. So that's actually how long it takes to complete a full cycle of tangent. It's only pi units. So one thing you might be thinking right now is that, well, when we learned to graph sine and cosine, both of those graphs had a period of 2π. So why all of a sudden is this one function different? So this has everything to do with actually which functions are positive in which quadrant. So if you guys remember, we do that ASTC to remind us which functions are positive in each quadrant. So if you look at the pattern of just the sign for each function, let's do sine, and then we'll do cosine, and then we'll do tangent. You can see that the patterns are different. So when we're working with sine is positive in quadrant 1, it's positive in quadrant 2, and then it's negative, and then it's negative. So it actually would take a full rotation for it to start that pattern again. It goes positive, positive, negative, negative, positive, positive, negative, negative. So you do need to rotate 2π before it can repeat that pattern with the signs. Now if you look at the sign, the SIGN sign of cosine in each quadrant, sine is positive in quadrant 1, it's negative in quadrant 2, it's negative in quadrant 3, and it's positive in quadrant 4. So if the pattern here is positive, negative, negative, positive, it takes a full 2π for it to repeat that pattern. So positive, negative, negative, positive, positive, negative, negative, positive. Now let's look at the sign, again the SIGN sign of tangent in each quadrant. We see in quadrant 1, tangent is positive. In quadrant 2, tangent is negative. In quadrant 3, tangent is positive, and in quadrant 4, tangent is negative. So look at the pattern here, positive, negative, positive, negative. So you can see it actually only takes tangent pi units to start repeating itself. So that's why the period for tangent is shorter than the period for sine and cosine. So that's just a little extra bonus stuff, but it is really important to remember that this period for the parent function is different. And then the next thing we're going to talk about are the asymptotes. So you can see that our asymptotes are repeating. The asymptotes are exactly pi units apart, or whatever the period is for your given tangent function, that's how far apart your asymptotes are going to be. Now if we want to find a way to describe our asymptotes, well, you might be thinking, how do I do that? There's an infinite number of asymptotes. So there is a way we can write this. So first, you need to know that we're going to be defining the variable n as any integer, or all integers. So when we're describing a repeating asymptote, first we would just describe any single asymptote. So pick any one, it doesn't matter. So I'll just say x equals pi over 2. And then I know it's repeating every pi units, so I could say plus pi times n. So if I do plus pi times n, that's essentially saying every positive or negative multiple of pi, right? Because n can be any integer. So n can be 1, so I could add 1 pi. N could be 2, I could add 2 pi and there would be an asymptote. N could be negative 5, I could subtract 5 pi and there would be another asymptote. So essentially you will say plus and then the period times n, and that will allow this asymptote to repeat every single period, again because n represents all integers. Okay, now that we know how to describe the period and the asymptote equation for our parent function, let's talk about what some of these transformations will do in terms of our graph. So we will see reflections, those reflections over the x-axis. Then we will also see the a value. So that a value is a vertical stretch. I know for sine and cosine we would call this our amplitude, but tangent functions don't have an amplitude. But what that a value will affect is the vertical distance of our points, of course. So I like to look specifically at these points that are exactly halfway in between, like I'll call this our midpoint and the asymptote. So you can see that we go through that point pi over 4, 1, and negative pi over 4, negative 1. So if you look at the point, again, that's exactly halfway between, which in this case is pi over 4, this distance here is going to be a. And then this distance is also going to be a. So if we have a vertical stretch, like this distance here would go up, or if we have a vertical shrink, it would decrease. So that would cause your graph to, stretch out or shrink vertically. But just consider this distance, the point that's halfway in between the midpoint and the asymptote, that vertical distance is going to be a. So it would affect the point between midpoint and asymptote. Now, of course, it affects all of the points, but in terms of graphing, that's a key point that I use, so that's the point that I'm going to focus on. Now, if you look at our b value, remember that's a horizontal stretch or shrink, so this is going to affect the period, because the period is the horizontal distance of a full cycle. So again, we would just take the period and multiply it by the stretch or shrink factor. And just like sine and cosine have a quote-unquote formula, so does tangent. It's just your period divided by b, which again, you're just multiplying by the reciprocal of your b value here. Okay, the h is going to represent a phase shift, so it's a translation left or right. And then the k is going to be a vertical translation, so we'll shift our graph up or down. And in terms of graphing, I would say that you should start by shifting the midpoint up or down. Of course, it's going to shift all of our points up or down, but this one will specifically, I start by shifting that midpoint. Oh, and then there's one extra thing we need to add for h. Since it is shifting our graph left or right, it is also going to shift the asymptotes along with the graph. So we need to be aware of any shift in terms of the effect on the asymptotes. Okay, we're going to start by graphing these functions using a table of values. So here we're actually going to try to graph 3 full periods of our function. So when we're using a table of values, we start by graphing, or by finding a couple key points from our parent function, so which would be tangent of x. So I'll use negative pi over 2, and then we'll say undefined. And we know that's an asymptote. So our asymptotes are going to change in the same exact way that our coordinates will change. So by including them in the table of values, it will change them in an appropriate way as well. And then we have negative pi over 4, negative 1, 0, 0, pi over 4, 1, and pi over 2, undefined. And I see that I do have a horizontal change. We have a horizontal shrink by a factor of 1/2. So all of our x values will get multiplied by 1/2, as well as our asymptotes, because those will be shrunk horizontally as well. And then we do have a vertical stretch by a factor of 3. So we could say 3y. So again, I'm going to take all of my x values and multiply them by 1/2. So we have negative pi over 4, and then we have negative pi over 8, 0, pi over 8, and pi over 4. And then let's multiply our y values by 3. Undefined stays undefined, and we have negative 3, 0, 3, and undefined. So in this case, you can see that we have the coordinates negative pi over 8, 0, pi over 8. So I think that'd be a good way to scale our x-axis. And then if this is pi over 8, that would make this pi over 4, which is where I have an asymptote. And then I also have an asymptote at negative pi over 4. And now we can plot our coordinates. So we have negative pi over 8, negative 3, 0, 0, and then pi over 8, 3. Then I know that our graph is going to eventually travel along our asymptotes. This one's a little tricky to graph. The more stretched out they get, the harder it is to show that real shape of your tangent function, but just do your best. We have something that looks like this. Now this is just one full period, so we do need to repeat it. So you'll see, actually, if you look in between our asymptotes, we do have 4 quadrants. It's 1, 2, 3, 4. There are 4 areas. So we can kind of repeat that pattern. 1, 2, 3. If I add another tick mark here, I can add another asymptote. 1, 2, 3, 4. And then I can repeat this pattern. So I'm going to be down at negative 3, and then at 0, 0, and then up at positive 3. Can make that tangent-shaped graph. And then I can do the same thing on the left. I can count 1, 2, 3, 4. I'll have another asymptote here. And then again, that same pattern down at negative 3, 0, and positive 3. There you go. We have 3 full periods of our tangent function. So here we can look at our graph to determine the period. I can see that my asymptotes are at negative pi over 4 and pi over 4. So that means the full distance from here to here would be pi over 2. But remember, another way you can find that is by starting with the original period, which was pi, and multiplying it by our shrink factor. There's a horizontal shrink of 1/2, so our period is pi over 2. Here we don't have an amplitude, so let's cross that off. We shouldn't have an amplitude for tangent. And now let's just describe our repeating asymptotes. So remember, we start by defining one asymptote equation. So we'll say x equals pi over 4, and then I know that it repeats every pi over 2 units because that's the period. So I say plus pi over 2n. And remember, n represents all real integers. All right, so go ahead and pause the video and see if you can give this one a try on your own. All right, go ahead and check your work here. So you can see here we actually have a horizontal stretch by a factor of 2, which is why our period is pi instead of 2 pi. It's doubled. And then we have a vertical reflection and a vertical stretch by a factor of 2. So you can see that now our asymptotes are going to be at negative pi and pi. And then those halfway points are going to be negative pi over 2, 2, and pi over 2, negative 2. So you can see because of the reflection, now we have this decreasing graph in each period instead of an increasing. And you can see that these points here are up at 2. So it's doubled due to the vertical stretch. So much like we did when we're graphing sine and cosine, I don't want us to necessarily rely too heavily on using tables. We can kind of just use what we know about transformations and how our tangent functions work. So I would say when you're graphing these, I would always start with the asymptotes. So that will involve, of course, finding our period, because the period is the distance between the asymptotes. So if you find your period, You go half the distance to the right and half the distance to the left of your y-axis, because your asymptotes should be kind of centered around the y-axis. So again, find your period and go half the distance to the right and half the distance to the left. That's where your asymptotes will be. Now, if there's also a phase shift, which remember is the shift left or right, then after you've placed them according to the period, then you would shift them left or right. Again, that occurs after you apply any period change. Another tip for scaling, much like we did when we graph sine and cosine, if you take your period and you divide it into 4 pieces, that's a really good way to scale your x-axis, and it will make the graphing much quicker and easier. So once you have your asymptotes and your scale, if you find a point exactly halfway between the asymptotes, that's kind of like our midpoint, or it's kind of like a starting point. We know that it's going to be on the x-axis unless we have a shift up or down for a vertical translation. And then you kind of find those quarter way points, so the point halfway between the midpoint and each asymptote. And then the vertical distance there is going to be the A value. So like in the last example, remember we had that vertical stretch by 2, so those quarter way points were up at 2 and -2. So this is kind of the process that I follow. I think it'll make a lot more sense once we do a couple examples together. All right, so let's look at this first one. We have -2 times the tangent of pi x plus 1. So first we need to figure out where our asymptotes will fall. So that would involve us finding the period. So here I can see that we have a horizontal shrink by a factor of 1/2. So if the period, 1 over pi. So if our period from the parent function is pi, I multiply that by the shrink factor, and I see that our period is going to be 1. And we won't have an amplitude here, so I cross that off. So since our period is 1, I'm going to start at the y-axis, and I'm going to go half that distance to the right and half that distance to the left for the asymptotes. But also, so I can scale it, take your period and divide it into 4. So I'm going to count by 1/4. So each tick mark on my x-axis is a quarter of a unit. So again, if I go half this distance to the right, I'm at 1/2. That's where one of my asymptotes will be. And if I go half that distance to the left, there's my other asymptote. And then you could see that the distance from here to here is 1. We can kind of continue this pattern on. Since it's been split up, our period has been split up into 4 parts for the scale, I just go 1, 2, 3, 4, and that's where my next asymptote will be. And then 1, 2, 3, 4 to the left, and I have an asymptote here as well. So now I need to find that midway point. So I know there's going to be a point that is exactly halfway between my asymptotes, such as here. Usually it would be on the x-axis, but here we have a shift up 1. So I'm going to actually have a point right here, like this. And then I know that I'm going to have a point exactly halfway in between our midpoint and the asymptote. So it's going to be somewhere on this line of x equals 1/4. But we know that the vertical stretch and the reflection can affect where those points are. So since I have -2 out front here, I'm actually going to go from my midpoint here, and I'm going to go down 2, and then over 1, and that's, or over 1/4, and that's where my next point is going to be. So see, the vertical distance here matches your vertical stretch, and we're going down to the right because of the negative. I know tangent usually is an increasing graph, but this one is reflected. And again, this vertical distance between your midpoint and this quarter point is also going to be 2. So I'm going to be all the way up here. So this is at -1/4, 3. And now I'm just going to do my best to kind of connect the dots to make that tangent shape that I know looks something like this. And we can repeat that same pattern in each of our areas between our asymptotes. So to the right, again, halfway in between, we're going to be up at 1 due to that vertical shift. And then the distance here, this vertical distance, is 2 because of the vertical stretch. Then I have a point here. And then we connect the dots. And then we could do this last period. So here's my midway point. Then I go up 2, for my quarter waypoint, and I go down 2 for this one. And again, just do your best to try to make that tangent shaped graph. Sometimes a little hard to do. There you go. So for our asymptotes, again, we have an asymptote at 1/2 and -1/2, and then we have one at 3/2 and -3/2. So the way we would describe that, name any asymptote. So you could literally any of these on here or any other one that exists. So I'll just say x equals 1/2. And then I see it's repeating every 1 unit. So I would just say plus n. Remember, n is any integer. So if I add any integer, so any positive or negative counting number, I will hit another asymptote. Okay, let's try another one together. So here I have a shift to the left, so this one's going to be a little bit trickier with our asymptotes. So we could start by looking at the period, and since we don't see a b value, the b value must be 1, so our period is unchanged from the parent function. So I think a good way to scale our axis is going to be to count by pi over 4. So still divide your period into 4 parts. So we know that typically I would take our period and split it in half, and I'd go half that distance to the right and half that distance to the left. So I know that I would have one at pi over 2. However, we need to shift our graph to the left pi over 4. So instead of being at pi over 2, I have an asymptote at pi over 4. And then I know since my period is pi, I go pi units away, and that's where my next asymptote will be. So if I go 4 tick marks away, that's where my next asymptote will be. So again, it's usually centered around the y-axis, but if you have a shift left or right, it's going to then look, it's no longer going to always be centered around the axis. So that will only happen if you have a phase shift. And then I can go maybe 4 tick marks to the right. Notice this one we're just graphing 2 full periods, and I have another asymptote here. So this is plenty for us to graph 2 full periods. Again, I'm going to cross off amplitude because we don't have it. So now I need to find our starting point. So I know I'm going to have a point exactly halfway in between our asymptotes. So it would be here at negative pi over 4. But I see that our graph is shifted down 2. So I'm actually going to have a point right here at negative pi over 4, negative 2. And then for my quarter waypoint, so for here and here, at 0 and negative pi over 2, I know the vertical distance from my midpoint is just going to be 1/2 because I have that vertical shrink. So I'm going to go half a unit up and then to the right, 1 tick mark. And then I go half a unit down and then to the left by pi over 4, or whatever our scale is for our particular graph. And then our graph will look something like this. So you can see that it's a lot flatter looking due to that vertical shrink. And then we can replicate that in the next area for our second full period. So again, our midpoint is down 2 units. And then I go up half a unit and then to the right by pi over 4. And then I go down half a unit and then to the left pi over 4. And now I have 2 full periods of our tangent graph. So to describe these repeating asymptotes, again, this one's at pi over 4, this one's at 5 pi over 4, this one's at negative 3 pi over 4. We can name any asymptote. So maybe this one I'll just name negative 3 pi over 4. Again, any asymptote that you see or that you know exists, you can start with. And I know that they're all pi units apart, so I would just say plus pi n. Again, we could describe it, we could say plus pi over 4 plus pi n. That would give us the same set of asymptotes. So it doesn't matter which one you start with, as long as you define one, and then you pretty much say how far apart they are, so you multiply that by n, which represents any integer. All right, go ahead and pause the video and give this example a try on your own. All right, go ahead and check your work here. For the asymptotes, I just gave 3 different examples of what could work to describe those repeating asymptotes. But here you can see that the b value is 1, so our period is still pi. That doesn't change. So I know that I would have asymptotes at pi over 2 and negative pi over 2. However, we have a shift to the right pi over 2. So if you take this one that was at pi over 2 and you shift it to the right 2, you have one at pi. And then I know that they are pi units apart, so I'd have one at 0 and negative pi, and that would continue on. And you find your halfway point in between your asymptotes. There's no shift up or down, so it stays at the x-axis. And then since there's a vertical stretch by 2, for those quarter waypoints, the vertical distance here and here is 2. So from the midpoint to the quarter point, the vertical distance should match your vertical stretch or shrink. All right, so now we're going to try one that's a little bit trickier because you'll notice here we have a b value and an h value. So just remember, whenever you see this, the first thing you need to do is separate the b from the rest of this binomial, so we need to factor it out. So we're going to factor out pi, and when I do that, what I have left is x plus 1/2 and plus 1. So remember, if you just look at your graph and you're maybe rushing or you don't catch that you need to factor this out, you're going to tell me that your graph shifts to the left pi over 2, but really it only shifts to the left 1 over 2. So you need to be really careful about that first step. Okay, so let's start with our period. So I can see that there's a b value of pi, so you take your original period and you multiply it by your shrink factor of 1 over pi, and we have a period of 1. So that means I'm going to scale my graph by 1/4 the unit. So to place my asymptotes, I know that typically I would go to the right half and to the left half, because I take my period and I split it in half. So I would have one here at 1/2, but I can see that my graph is being shifted to the left 1/2 of a unit. So again, instead of being here at 1/2, I have an asymptote at 0. And I know that they are all going to be 1 unit apart, so that's 4 tick marks for our scale. So I have an asymptote at 0, I have an asymptote at x equals 1, and I have an asymptote at x equals negative 1. Okay, so now that I have my asymptotes, I can find my midway points. So I know there's going to be a point at x equals 1/2 that would typically be on the x-axis, but we have that shift up 1. So my midway point is going to be at 1/2, 1. And then I see that I don't have a vertical stretch or shrink, but I do have a vertical reflection. So from here, instead of going up 1 and then over 1/4, I'm going to go down 1 and then over 1/4. And then on the other side, I'll go up 1 over 1/4. So the graph looks something like this. Then we can repeat that same thing in the next, between the next 2 asymptotes. So right here. And we get something that looks like this. Again, there's no amplitude for a tangent graph, and for our asymptotes, again, we can write these in a number of ways. Since they're all just exactly 1 unit apart, we're just going to take any asymptote and then add n, which is any integer. So we could just say x equals n. We could say x equals 1 plus n. We could say x equals negative 1 plus n. Any of these are valid ways of describing this repeating asymptote. Okay, so I have this last one for you to try on your own, so please pause the video and give it a shot. All right, so go ahead and check your work here. So you can see first I factored out the 2. So we do have a horizontal shrink by a factor of 1/2, which is why the period is pi over 2. So you can see I scale my graph by pi over 8. Now this one's actually kind of interesting because since the shift is the same as the period, it actually doesn't even look like we shifted it. So imagine, right, we would typically have 1 at pi over 4 and negative pi over 4. And then if you shift it to the right by pi over 2 units, it ends up really in the same place it would originally be. So anytime you see a shift that is equal to the period, it's almost like the shift doesn't apply, or you can even think of it like that if it helps. And then we have our midway point that's at 0, negative 1 because of the vertical shift down 1. And then for the points a quarter of the way, remember with the vertical stretch, that means the vertical distance between the midpoint and the next point is going to be 2. So I go up 2 and then over pi over 8 and then down 2 over pi over 8. And here's just one way you could write your repeating asymptote. So I just did pi over 4, this asymptote, plus pi over 2n. So you should have plus pi over 2n because it repeats every period. All right, so that is all for today's video. Thank you so much for watching.